get our last. We're going to record this to our computer. All right. Well, then I'm going to say hi to all of our friends. So my name is Thomas with the Museum of Discovery. I'm very thrilled that we get to connect with you all with our virtual Awesome Science program here today. We have relocated because of an unfortunate flood at the museum, but the zoo has been oh so kind to lend us this space here today. And it is my job to get you all the best shots possible so you can see the most awesome of the science. So without further ado, I'm going to turn it over to that guy right there. That is the one, the only, the incredible Mr. Sean Carlock. And before he starts, one of the things I wanted to tell you guys is that we have been sponsored to bring this to you from PPG. So we are super happy that they were able to provide this program for you all. So anytime you see somebody working there, give them a shout out, tell them thank you. We just wanted to give them a good holler because we are so happy that we can connect to you guys. Now, with that being said, I will turn things over to Mr. Sean Carlock.
Fantastic. Thank you very much, Thomas. Good morning and welcome to the Little Rock Zoo. Thank you to them for having us out here as a place to set up and show you guys some of the coolest things that we offer at the Museum of Discovery. I'm going to show you, like I said, some of the coolest, but this first thing is the absolute coolest thing you've ever seen. I would go so far as to say that this is the coolest thing that any of you will ever see in your entire life. Now, I know that that is a pretty bold statement, but I will prove to you that it is true. But what I'm going to show you is a little bit dangerous. So I have a few things here to help protect myself from what we're about to see. First, these to protect my eyes. These to protect my hands. Because like I said, what I'm about to show you is extremely, extremely dangerous. But how would you feel if I told you that right now you're completely surrounded by it? It's in the very air that you breathe. But currently, it's in its gas form. You guys talked about the different states of matter, solids, liquids, and gases. Well, when this is a gas, it's completely harmless. It's in the air we breathe, and it doesn't harm us at all. But if you take a gas and get it very cold and put it under extreme amounts of pressure, you can condense that gas down into a liquid. And that's what I have right here. Inside of this doer, I have a liquid that is very, very dangerous. This liquid is called liquid nitrogen. So the gas we were talking about, nitrogen gas in the air that we breathe, in its liquid form, negative 321 degrees Fahrenheit. So that is why this is the coolest or coldest thing you will ever see in your entire life. Now, there's nowhere here on Earth that liquid nitrogen can occur naturally. And as I pour this, it kind of looks like it might be water. But water does not act like this. You can see it kind of jumping out of the top of our beaker there. Now, maybe you've seen water do that before. If you get water very, very hot, it will start to boil. And that is what our liquid nitrogen is doing right now. Now, how can something that is negative 321 degrees Fahrenheit be hot enough to boil? Well, the temperature in this room and of this beaker are so much further above what our negative 321 degree liquid nitrogen is that it causes that liquid nitrogen to boil. Now, there are a lot of very important things that liquid nitrogen can be used for. They use it in the medical field for cooling down large magnets in medical equipment. You can use it to burn off warts. But here at the Museum of Discovery, we just like to put things in it and see what happens. So I've got a few things I'd like to show you. Now, when we talk about solids, liquids, and gases, what do you think this would be? Now, a solid is something that is able to hold its own shape, right? Does this hold its own shape? It does. But does a solid normally do this? Yeah. So this would be a solid, but it's kind of a special solid. We call this a polymer. It's a chain of molecules that are allowed to move and bend and stretch. And that's what makes rubber bands very, very useful, is the ability for them to stretch and then go back to their original shape. What do you think is going to happen when we put this in our liquid nitrogen? Kind of hisses and bubbles and boils even more because of the heat that rubber band has in it. Put another one inside. And we don't have to leave them in there for very, very long because, like we said, this is negative 321 degrees Fahrenheit, and that is very, very cold. I'm going to take one of these out, and we're going to see if it still acts the same way that it did before. All right, here we go. 3, 2, 1, and oh, what happened? Just a little bit of pressure applied to that, and it caused that rubber band to shatter, to break into pieces. Now, when it gets cold, those molecules, they kind of huddle up like you might when it's cold outside. And they pull themselves really close to try to stay warm. And so when we tried to move them, they didn't want to move. Those bonds were no longer loose and stretchy. It caused our rubber band to become brittle, and it broke into a bunch of pieces. Now, if you missed that one, that's why we do it twice. Three, 2, 1. Look at that. All of those little pieces just shatter away. But after just a couple of seconds, it starts to warm back up again. And that rubber band becomes stretchy once more. Now, I've got another polymer here. Very much like our rubber band, it stretches. But this one's different because we can put something inside. Now, this is a balloon, right? Inside of a balloon, we could put a liquid, but generally you'll see them put gas inside. These in particular, people will take and twist up and make animals and things out of them. I've got a couple over here that I made ahead. I'd like to introduce you to my two friends, ketchup and mustard. Now, do you think the same thing that happened with our rubber band will happen if we try to put these guys inside of our liquid nitrogen? Do you think that they'll shatter into a bunch of pieces? Let's find out. Mustard first. In he goes. Squish him all the way down inside. Now, it shouldn't be possible for one of these to even fit inside of our beaker, let alone two of them at the same time. But watch, we can take the second one and feed it right down in. Now, listen close. I didn't hear any popping. But how many of you think that it's possible that the balloons did pop and the air came out and that's why they shrunk down and they're able to fit? Could be. Or maybe the balloon didn't pop. That's why we didn't hear it go boom. But somehow that air was able to escape out of that balloon as it got cold. Or perhaps the air is still inside. Seems kind of strange, doesn't it? How could the air still be inside of those balloons if they're so small and tiny and shrunk down? Well, what is air? A solid, a liquid, or a gas? It's a gas. And when you get a gas really cold, that gas condenses down and changes into a liquid. So right now, inside of those balloons, we have liquid air. And I can prove to you that it's still there. All we have to do is take the balloons out of that cold environment. Back into the warm air of the room, and that liquid air starts to warm up, starts to boil, starts to evaporate, changes back into a gas, which spreads out and takes up more space than it does as a liquid and fills our balloon back up the way it was before. Look at that. Now, that one's been in there a little bit longer. Do you think it's going to have the same luck? Let's find out. Back into the warmth. That liquid starts to evaporate, changing back into a gas, expanding, filling up that space, stretching the balloon back into its original shape. Isn't that amazing? That's how cold this stuff is. It can turn the air into a liquid. Pretty neat, huh? Now, polymers are fun, especially because they act differently when you put them into the cold. They lose their ability to stretch. They lose their elasticity. But I've got something else here that some of you might be familiar with. You ever been to one of those places where they have the big pits full of all of the balls that you can get in and climb around and have fun? I have determined through very careful scientific research that these are not good for anything but being put into a large pit for people to crawl around in. They're not heavy enough to throw. You can't really play catch with them. They don't bounce very well, so they can't really be used for that. But one good use I have found for them, putting inside of liquid nitrogen. Now, this is going to kind of do what everything else that we've looked at so far has done. Right now, the outside of that ball is getting very, very cold. The molecules are getting very close together. The outside of that ball is becoming brittle. On the inside, since the ball is hollow, there's air. Well, that air is also getting very cold. It's starting to condense down and become a liquid, taking up less space than it did before. That's going to create a little bit of a vacuum inside of our little ball. Now, I'm going to pull this out of here in just a second, and we're going to give it a good whack with our tongs, and you're going to see what happens once the outside of this ball fails. Watch what that vacuum does. Here we go. 3, 2, 1. It almost looked like it exploded, didn't it? Well, technically, it imploded. As the outside of that ball was punctured, it kind of went and collapsed in on itself and shattered into all of these little pieces. Made kind of a mess, but we'll clean that up later. Pretty cool, huh? I told you that this is the coolest thing you've ever seen and probably the coolest thing you will ever see. But I do have to admit, doing all this really awesome, cool science kind of makes me hungry. Do you guys mind if I pause for just a second? I'm going to have a little bit of a snack. I brought these for lunch today, but I think it'll be all right if I have one early. Cheetos. Love these things. They're so cheesy. The Puffs are probably my favorite. I like the crunchy Cheetos. I've never really had the spicy hot ones. Spicy's not kind of my thing, but I should caution you. It's not a good idea to have a snack while you're doing science experiments. If you were talking and not paying attention, you might accidentally drop something into whatever it is that you're working with, and that would not be good. Contaminates the experiment and it's a waste of a perfectly good Cheeto. Because you guys saw just how cold this is. You saw how it caused the very air inside of our balloons to shrivel up and to become liquid. What do you think would happen if I took that Cheeto out of there and put it into my mouth? Probably not a great idea, right? But it could be really interesting. After all, it is in the name of science, and I'm a trained professional. Okay, you've convinced me. Let's check it out. Super, super cold Cheeto. Experiment number 1. Oh, wow. That is a very, very cold Cheeto. And you could see how it was causing my breath to become fog. The moisture in my breath as I was exhaling was this big fog cloud that was coming out and flying through the air. Now, I had to take my mask off so you could see that, because this kind of helps to prevent all of that from coming out. And let's take a look at how it does that. I'm going to have another one of these, except this time, I'm just going to leave my nose hanging out. Watch what happens. Look at how far that still flies out, just from my nose, from breathing. Now, we'll do our last one, except this time, I'm going to make sure that I have my mask on nice and tight. And fitting over my mouth and my nose. And let's see what it does to that breath as I exhale. Boop. Come here. It didn't go quite as far, did it? It kind of stayed right here in my own space. That's why these are really, really helpful to keep from the particulates and the moisture in our breath from coming out and being transferred from person to person. A neat little experiment that we can show because of how cold our liquid nitrogen is, causing that condensation and that fog from the breath. Wow, that's a cold Cheeto. Now, I do want to make sure that you understand that that is exactly what I put in my mouth, a cold Cheeto. By the time that Cheeto comes out of that liquid nitrogen and gets set on the table, all of that liquid has evaporated. It can't exist in this warm space. That's why we have to keep it inside of this dewar. So I'm going to take what we have left in here, and I'm going to put it back into our dewar because I want to show you one more thing with it, but I'm going to wait. I'm going to save it, because it's my favorite, for the finale. And if I didn't put this back into our special container that helps to keep it cold, by the time we were ready for it, all of this liquid nitrogen would have evaporated. It would be gone. So we're going to put it inside. And look at this. There's snow on the outside of my beaker here because the moisture in the air got cold and condensed on there as well. Look at that. That is a cold, cold, cold beaker. You can see the snow on the outside. Huh. Now, you noticed how when I was exhaling and you could see my breath coming out, that it was really all over the place. Very, very turbulent air. We're going to talk about a way that air can travel in a lot more efficient manner. I'm going to talk to you guys about something called a vortex. Sounds pretty cool, doesn't it? Like some kind of evil space alien supervillain pirate. Vortex the Destroyer. Well, if I asked, what is a vortex? Could you give me a definition? It might be a little difficult because not everybody has heard of a vortex, or maybe not heard to it referred to by that name. If I said, how many of you have ever taken a bath? Well, hopefully all of you would raise your hand. See, when you get done taking your bath and you pull the plug, does the water just go straight down? Or does it do something on the way? It spins around, doesn't it? That is a vortex. Any spinning liquid or gas is a vortex. I can show you what that looks like in your liquid bathtub by using this super duper handy dandy, super high tech handheld vortex generator. Okay. It's just a couple of soda bottles that we stuck together. You could make something like this at home. Get a couple of empty bottles, put some liquid inside of one, put a little bit of food coloring in there so that we could see it better. Leave the other bottle empty. Now, if I wanted to get this liquid into this bottle, what should I do? Well, turn it over. Then the force of gravity helps to pull that liquid from one bottle to the other. But there's a problem. it doesn't really work very well. It drips a little bit, kind of glugs, but this isn't a very efficient way to get this water into that bottle. Reason for that being, is that bottle empty? It isn't, is it? It's completely full of air. There's a gas inside of this bottle that keeps all of that space occupied. So if we want this liquid to go into that bottle, the air has to go somewhere else. And when we turn it over like this, the liquid tries to go down, the air tries to go up, and they run into each other right here, and they kind of get stuck. That's where our vortex comes in. So if we give it a little bit of that spin that we talked about, and he's spinning liquid or gas, watch what happens. Look at that. Have you ever seen anything that looks like that before? Maybe a tornado? Well, a tornado is a vortex in the air. In liquid like this, we would call that a whirlpool. And right down the center of that whirlpool, there's a tunnel of air, kind of like a straw that allows the air to come straight up through while the liquid spins around and goes down the sides. That way they don't run into each other right here. They're able to exchange places much more efficiently. Now, I know that we said that a vortex is spinning liquid or gas, but it can also be some other things, specifically plasma. What is plasma? Well, what if I called it by a different name? What if I told you I could show you a vortex made of fire? Sounds pretty cool, huh? In order to do that, I need a couple of things. If we want to make fire, we've got to have a trash can. Well, you don't have to have a trash can, but in our case, it's going to help. Fire needs three things. One, being oxygen. Two, being some sort of a fuel or something to burn. In our case, we're going to use a little bit of isopropyl alcohol. I'm going to put that down here inside of my trash can. Now, the oxygen, well, the whole room has oxygen in it. Otherwise, we wouldn't be able to breathe. So we've got our oxygen, we've got our fuel. The last thing that we need is a spark or a heat source. We're going to use this lighter for that. So if we were to put our heat to our fuel, we could very easily create fire. But if we wanted to have a fire vortex, a fire tornado, we have to have rotation. Look at that. Look how it spins around and makes a big column, like a big fire tornado. Let's go the other way. Wow. Now, luckily, this isn't something that you're going to see often here in the States. If there was a big wildfire or forest fire, kind of like the ones they had recently in California, this might happen. If the winds were just right, it could whip those flames, that plasma, that fire, into a giant fire tornado. Now, in Australia, this happens much more frequently than it does here in the US. I think that that's one phenomenon I can live without, though it is kind of neat in a scientific setting. Fire tornado. Could you imagine if you walked outside and you saw that coming down the street? That would be terrifying. But why do we want to know about vortexes and how they move air? Well, because it lets liquids and gases exchange places more efficiently. But I'm going to show you another reason right over here. Using my cups of science. Oop. All right. Do you think that if I took a big, deep breath, that I'd be able to blow those cups over with my breath? Let's give it a try. Not so much. Because remember with the Cheeto, how my breath kind of went all over the place. It's hard for me to focus it on one spot with enough force to knock over those cups. That is why I brought this. Another trash can. But this is no ordinary trash can. This has been modified into a bona fide vortex cannon. We put a hole in the bottom of it here and put some rubber sheet on the top so that I can play it like a drum. And when I hit that drum head, it forces the air inside to come out through this hole. Now, thanks to Bernoulli, we know that moving air has low pressure. Basically, it's going somewhere. It can't push out to the things around it. So the higher pressure atmosphere around it swoops in to take up that space. And as it does, it meets that column of air and starts to move with it. And eventually what you get is this rotating gases vortex that pushes that column of air forward and allows us to do cool things like this. Timber. Oh, pretty cool, huh? Now, only problem is we can't really see what our vortex looks like, can we? I could do this all day and we'd never see it because you can't see the air. If you go like this, you can feel it. We can see it when it moves other things, but we can't see the air itself unless we add something to it. Now, this is a fog machine. And this is going to create some artificial fog for us that will allow us to see our air. Just like that fog that was created with my breath when we used the Cheeto. All right. So tell me now, what does it look like? Look at that. Now, some people say it looks like a ring. I've heard people say it looks like a halo, a circle. My personal favorite, it looks like a donut. Now, in science, we call that donut shape a toroid. So here's some vortex toroids that we're shooting out. Now, we said that in the air, a tornado is a vortex. Does that look like a tornado? It really doesn't, does it? But if you could take the top and the bottom of a tornado and twist them around and connect them together, that is exactly what it would look like. The whole outside edge of that toroid, or that little vortex, is spinning. I love that. So neat. I could do this. What's that? Do a slow one. See if I can get one to go through the other one. Oh, so cool. Spinning gases, spinning liquids, spinning plasma, vortexes. Oh, I love my job. And I told you I was going to show you my favorite thing last for our grand finale, and I'm going to. But to do that, we've got to get back our liquid nitrogen, negative 321 degrees Fahrenheit. Have to make sure that we're safe. I've got my gloves. To do this successfully, we have to have just the right amount of liquid nitrogen, about 400 milliliters. which is a lot easier for me to see now that the snow is gone from our beaker. We're going to measure this out. Oh, that's not even close. You guys say when, okay? Oh, that's a little too much. Pour out just a little bit of this. Look how quickly that froze to the bottom of that. There we go. Now, over here to the side, I have a tea kettle, and that heats water up to the temperature of boiling, 212 degrees Fahrenheit. I'm going to combine that with my liquid nitrogen, 212 degrees Fahrenheit, negative 321 degrees Fahrenheit. It's a difference of over 500 degrees. If I did that inside of this beaker, it would shatter. So we're going to put it inside of this big metal container, inside of a metal pitcher. I'm going to grab some of our hot water. $212 degrees. All right. I hope you guys are ready for this. Like I said, this is my favorite. It's going to be great. But I need everyone's help to count with me from 5, 4, 3, 2, 1, and did you see that? Look at all of that fog we've created. Now, the second that we put that hot water into our liquid nitrogen, it caused all of that liquid to immediately evaporate and become a gas. And remember how we talked about how the gas takes up a lot more space than what the liquid form does. So it wasn't able to stay inside of our little pitcher. It had to escape and come out. Now, because of the shape of the pitcher, that makes it shoot upwards. That was that big cloud of fog that you saw coming up, was all that nitrogen gas just rushing out. So all we have left in here now is maybe just some really cold water. You can see how cold it is as it falls down because it's very, very heavy. Just falls out. Sometimes we even get ice down in the bottom of our pitcher. You can hear it crackling. Look at that. Oh, there is. I don't know if can you see the ice in there? Look at that. Have you ever seen ice form so quickly? Instantaneous ice. That's how cold this is. And that's why I told you that I was about to show you the coolest thing you've ever seen in your entire life. And I hope that I was able to prove that. So thank you guys very, very much for sticking with us through this awesome science demonstration. And Mr. Thomas is going to help you guys. If you have any questions, feel free to ask those. Teachers, if you want to unmute your microphone, if one of the students has a question, or if everybody remotely today? Okay.
Yes.
So if you've got a question.
This is our virtual day. This is our virtual. So they're all, well, the ones who are in here are virtual right now. So they're at their own Chromebooks.
Okay. So yeah, so if you've got a question, can we see? We can't see everybody. We don't have cameras on.
Hey, put your cameras on. Let me put mine on too.
Yeah, if you could turn your camera on, and if you've got a question, just raise your hand, and Mr. Thomas will call on you. And when he says your name, go ahead and unmute your microphone and then ask your question. Okay, it can be about one of the experiments that we did here today, and we'll answer those questions.
That was really good, by the way. I love that.
Well, thank you.
Yeah.
I was going to say, I think we first off need to give Sean a big round of applause for a fantastic, awesome science show. I really enjoyed that.
Yeah, that was excellent. We really appreciate it. That's a
All right,
change
so
up to our normal Zooms that they're not always so happy about. So it's great.
if we made a compelling and fun Zoom session, then hey, we've won.
Absolutely.
So what questions do we have about what you saw in our awesome science program today?
Guys, y'all have any questions? Anything?
How did y'all get
What was your
that?
favorite?
How did y'all get
Say
the
that again,
liquid
Isaiah.
nitrogen? Where did y'all get that liquid
So-
nitrogen?
Like we talked about, liquid nitrogen doesn't occur anywhere naturally on Earth. There's nowhere that's cold enough. So all of the liquid nitrogen that we use has to come from a laboratory. They have to have special machines that they pipe in a bunch of nitrogen gas and they get it really, really cold and put it under a lot of pressure. And as they release some of that pressure, that pushes the temperature down even further until it finally gets cold enough that it condenses down and liquefies. Now, this isn't something that you're going to go and purchase in the science aisle at Kroger. This is something that you do have to have special permits and things to have, because it is very dangerous, not just because of how cold it is, but because of, remember how we talked about a liquid takes up less space than a gas? So as this heats up, it's expanding. So if you don't have it in a proper container, that pressure is going to build up and build up and build up and build up until eventually it would go boom. So there's danger of that. And then one Thomas pointed out to me a few programs ago was, if you were in a smaller room and you spilled a large amount of liquid nitrogen, as it changed into nitrogen gas, it would displace the oxygen in that room, and you wouldn't be able to breathe, because you have to have that oxygen in order for your, to function. So there's a lot of different reasons that this is a very, very risky and dangerous substance. So we make sure that we take all the proper precautions with it when we use it, but that's why you won't be able to just go out and buy some.
Thanks for that question, Isaiah. What's our next question for today?
Anything else, guys? There's no question that is silly to ask or wrong. So if y'all have anything, now's the time. Anyone? They're a little shy on Zoom.
Hey, I understand.
I understand.
It's a different platform. Does anybody have a demonstration that they thought was their favorite?
I thought
fire.
The fire.
All right, I heard Derica said the fire. Isaiah, what was your favorite?
the last one.
Nitrogen cloud? Oh, yeah.
I like the Cheeto.
Say that again for me, Janae.
When he had ate the Cheeto.
Yeah, that one's one of my favorite too.
That's
I
one of
really
my
like that
favorites
one.
too. It's very tasty.
And the weird thing about it is it tastes just like a normal Cheeto. It's just super cold. So it's kind of this weird sensation of you'd think it would taste different just based off of how weird it's making the fog look, but it just tastes like a Cheeto.
Very cheesy.
Anybody else have a favorite that they didn't mention? What about you, Mrs. Campbell? What was your top?
Oh, I'm with them. The Cheeto thing was so good. I've never seen that before.
Well, once the museum reopens and we can go on field trips again, you'll need to come to the museum and we will let you, Miss Campbell, eat a frozen Cheeto.
Absolutely.
Do y'all
I'm
do you
very,
guys
very
still
good at sharing.
Yeah, do y'all have I think it was y'all. Do y'all still have like the space food thing? Was that y'all, like you have some that you can buy?
Our Explore store has done a few different versions of space food, like some freeze dried stuff, but we don't have like the frozen, like the actual frozen, like Dippin' Dots type food.
Okay.
But we have it. Yeah.
We will
Freeze-dried,
definitely make
you may learn, is not necessarily the most tasty, but it is
Oh,
kind of
yeah.
fun to experiment with it.
And
I
the
would
thing
think
that I find
so.
most interesting is in just about every science center everywhere, you can probably find freeze-dried ice cream, which has never been ever on any space shuttle ever.
Really?
So yeah, I found that absolutely fascinating, because growing up as a kid, that was such an iconic thing of, this is what the astronauts eat.
Yes.
But I think there was one mission that actually had ice cream, but it wasn't freeze dried. They had a little freezer that they put on the shuttle and had real ice cream in space. But
Well,
Oh.
my goodness. Yeah, that I grew up thinking it was too. Like I was sure that's what they ate. Guys, did y'all have anything else? I know they are busy, so we don't want to hold them up. Any other questions or comments? Okay. Yeah, thank y'all so much for doing this.
You
I
are
know they
most
enjoyed it and I
welcome.
did too.
Well, thank you guys for joining. And once again, thanks to PPG for providing the funding to bring us to your classrooms and homes here today. So from Sean and myself at the Museum of Discovery, we thank you guys and hope y'all have a great day and weekend.
Thank you, you too. Bye-bye.
All righty. Bye-bye, y'all.